confusing me from the beginning.
Yeah.
I think I understand it. I just want to make sure I
Yeah.
have it right. The word experiment, you don't mean experiment. I mean, that is, you don't mean the general class of experiments. I might be interested in how a tub of water works, and I experiment with it. Then the target system is the thing I'm looking at. That's what I normally think of as an experiment. You're talking about small-scale models,
Right.
physical models of larger-scale objects. That's what you mean by an experiment?
That, I mean, that could be an example of an experiment. I'm not sure.
I take it most experiments are not like, you know, a tub of water, and you wonder how that tub of water behaves, so you experiment on that tub of water, right? Most experiments are, you're interested in how electrons behave, so you have a few electrons that you...
If I do a scattering experiment, it's not a model of something else. I want to know how things scatter. I mean, it just seems to me, I just want to understand the language.
Yeah, but the target system is not the object system itself in that case. You're interested in electrons in general. You're not just interested in those electrons.
You have to have some reason for thinking that electron is representative of all the other electrons. I mean,
Yeah.
that might be a really trivial background knowledge in that case, but it is background knowledge.
Yeah, yeah.
I have a similar problem with simulation. I mean, people were doing simulations since ages. Planetary was done in the 18th century doing by hand. I don't see any distinction between simulation and theory or models.
Well, we're going to come
I
to
mean, we
that.
are just trying to get...
We're going to come to that.
So
I'm
this
going to.
sounds funny, the opposition between theory and experiment then.
Well, I'm going to come back. I'll come back to these questions, but this is well. What I'm trying to just outline here is a way of thinking about the difference between experiments and simulations in purely epistemic terms, in terms of what background assumptions are needed to ground the suitability of application of the object system for the target system. That's the general idea. That's the idea behind this kind of approach, as opposed to just taking materiality or similarity or some other thing, which I don't think is really essential to the difference. I'll come back to the questions that the question was just asked later. The point I want to emphasize is that we're often very confident in the reliability of principles for building simple models, for instance, simple Newtonian dynamical models. And I think it's because we're very confident in these model building principles and their reliability that we think that, you know, for instance, models of planetary motion are very suitable and very applicable back to the real world.
But this is what you are calling secure. This is
Yeah.
secure.
Yeah, I think we're very confident in the reliability of those methods for putting together these simple models. The n-body simulations that, you know, that Priya was talking about and that other cosmologists talked about, they're also Newtonian models. They're just really big ones. 10 billion bodies over, you know, a very large cube where you get 25 terabytes of data from the simulation. That's big, and I think the question, for me, the question is just going to be how warranted are the requisite background beliefs for grounding the suitability of the object system for the target system. That, to me, is the real question. So we should just be asking how secure or warranted are these background assumptions.
Isn't that just asking if Newton's laws are applicable to large aggregate systems? Isn't that the proxy for that question?
I don't think it's just that. I mean, you'll know more than I will, right? I mean, as to exactly what goes into constructing these models. That's just an invitation to sort of talk about what these background beliefs are in the case of the n-body simulations. It's not merely that. I mean, I'm guessing it's more than that. But to me, that's the question, right? That we're going to need to ask epistemologically. And also, I'm not clear exactly what the simulations are used for. Maybe that's another invitation to for you to comment on that. Okay, this is if you think of it in purely epistemic terms like this, it's not that easy to really come up with significant differences between experiments and simulations. Here's one difference that I think does exist. Experiments are often useful for giving crucial tests of hypotheses or models or hypotheses or theories. And one presumes that this is not a role that's ordinarily played by simulations. And why? Because the applicability of the simulations already assumes that we know a great deal about how to build good models of the features that we're interested in learning about. So one question is, what are the models doing? What are the simulations doing? Are they just calculational devices for churning out predictions? Or are they doing something over and above what normal simulations do? Do they actually somehow participate in the generation of crucial tests or something like that? That would make them really weird. That would make them different than other simulations. But
I would argue they are the only test, not crucial test. That's where I defer.
so, okay, well, no, that's good. I mean, that's good. That's good. But I think, so here's a difference between experiments and an epistemic difference that I can see between experiments and simulations. Maybe there are others, and so the question is, why is it that the n-body simulations are peculiar, if they are? This is just an invitation for you to comment on that, since you're the expert on that. Okay, so just finally some questions for discussion. How confident should we be in the reliability of these model building principles here in this particular context? Are the simulations just merely tools for calculating what certain models predict, which we can then check against astronomical observation? You might wonder if that's true, then do they really deserve to be called simulations in some, I mean, not really sure. Maybe they're just calculational devices. And finally, I mentioned this before, you mentioned a lot the uniqueness of the universe, or that there's only one universe. And I guess that's also related to we can't perform controlled experiments on the distributed universe, the actual universe or something like that. And you thought that was problematic. Maybe it is, but I don't see why it makes these simulations more problematic than, say, any other simulation of a historical evolution that's actually occurred. I'm not sure what's special about these. Maybe there is something, but again, that's an invitation to say what's special about these as opposed to just other historical simulations or models in any historical science, not just cosmology. Right, so that was it. Those are my comments. I do have one animation that I had to show an animation just because we're talking about simulation. This one is by Di Matteo, and it visualizes the full-time evolution of a galaxy collision, even though there are really no small-scale collisions, I guess, but two big
galaxies collide because they have gas, which is barrier.
Galaxies collide, right, yeah, okay. So, two spiral galaxies with big black holes at their centers colliding, so this is kind of a cool, I just found this really neat that you could actually do this. And you could visualize it, and there's some really interesting dynamical things happen.
So you don't see the dark matter here at all. What you're seeing is the gas.
So I mean, I think it's amazing that you can, with this many bodies, actually do any kind of simulation at all of something that's physically complex.
Let me ask a question to see whether I understand correctly. If these galaxies consisted exclusively of dark matter, what would happen would be that the galaxies, nevertheless, they do collide and make some complicated motion because of their gravitational interaction, but just kind of two particles of dark matter, they would not interact significantly.
No, so what you would have is you would have the dark matter getting redistributed. So it would get pulled, you would see these tails and stuff in the dark matter because of gravity. It's all the tidal forces, right, that are doing the job here. And so you would see similar structure, but it would settle back into some kind of equilibrium distribution for dark matter that is pressureless.
So when you say they don't collide, that means they interact only by means of gravity.
Gravity and nothing else, yeah. And they remain pressureless.
So was this gravitational or was this more than gravitational?
This is hydrodynamic as well as gravitational.
Oh, okay.
Because it has gas. And this is also not from cosmologically correct initial conditions. So these are just two galaxies mocked up to be here, as you saw, with two big gas blobs, and then smashed. So what I've shown you are always starting from the correct initial fluctuation spectrum and following through. It's not computationally tractable to do this in that context.
Anyhow, I'll just finish by saying these are some interesting recent papers on the epistemology of simulation. There's a nice survey paper. This paper argues that materiality is not really what's making the difference. And Eric also has some similar arguments in his recent paper. So I thought these were really useful. This is a good excuse for me to start really getting into the epistemology of simulation.